This lesson is our third lesson on the applications of derivative. It's our actual last big application of derivatives. The first one was related rates types problems, where we found how fast an object was moving at an instant in some type of word problem. This is very similar to that. We're going to have some kind of word problem where we have to draw on our prior knowledge of algebra and geometry formulas and equations and use the calculus to solve these problems and answer this. These are called optimization problems. Whereas related rates problems, you want to find how fast an object is moving in an instant. Optimization problems, you want to find the best possible outcome. You want to optimize something. Whether it's a profit expression where you want to make the most money, cost expression where you want to minimize the cost spent. If you want to build something out of some material that you're given, you want to make it the biggest possible container, or you want to find the closest distance between a moving point and something else. So we're going to optimize, maximize or minimize using calculus. So your goal is always to maximize or minimize something, and it'll be stated clearly in the problem. You'll be given specific details about some value. They'll have to give you some information in order for you to find the best outcome for that specific situation. And you're going to use calculus to find the maximum or the minimum value, just like you would do during graphs. So here's a problem. A company wants to make a box with an open top and a square base. The company has decided it will use 108 square inches of material. What dimensions will produce the box with the maximum volume? So this company is going to make a box. It's going to have a square base and it's going to be open on the top so you can put things into it. The company's decided it's going to use 108 square inches of material, meaning this is the material we have to use. I want to construct a box. Square base, open on the top, so that I can fit the most things in it. I got this much material, I might as well make it as big as possible. And that's your goal here. You want to find the dimensions that will produce the maximum volume. In these optimization problems, you always need two equations. You'll need a primary equation and a secondary equation. The primary equation is what your goal is. I want to maximize volume. I want to minimize distance. I want to maximize area, whatever that is, whatever they say, to find the max or the min of, whatever you're trying to maximize or minimize, whatever you're looking to optimize, that's your primary equation. So we want a box with maximum volume, so the volume of a box will be our primary equation we have to work with. There will be a secondary equation based on the given information. They're going to give you some specific detail. In this case, you got 108 square inches of material to work with. So we're going to use that idea to develop a secondary equation. So, let's say we have a box like this, all right? Open box, we can put things in, assume the base is square. It's not perfectly square in this container, but you get the idea. This is what we're looking to build. We were given 108 square inches of material, and we want to build a box with an open top, square base that fits the most inside. The 108 square inches of material, that's the amount we make this out of. That's going to be the same as the surface area. The material we use will be the surface area of this box. You can tell it's going to be an area because it tells you some square inches. So to find the surface area of this box, we're going to use the dimensions x by x for the base. Since it's a square base, the length and width will be the same. So we're going to say x by x is our base, and the height of the box we'll call h for height. So, to find the surface area, the total surface area, you would find the area of the base, which is x by x, so you have x squared. If each one of these sides was the same, it would be x by h. And since it's a square, all the sides are the same, the height's obviously the same all the way around, so your four sides that are each x by h. So your total surface area will be x squared because of the base plus 4 times the area of each of those sides. The volume of the box will be length times width times height. Volume of any rectangular solid, length is x, width is x, height is h. So the volume of your box is x squared times h. So now you have your two equations. Primary, what you want to optimize. Secondary, the information they gave you, which was about surface area. Now, as you see, volume equals x squared h. V, x, h, you have three variables. Well, in your previous few sections, When you were finding max and min values, max and min points, when you use first derivative test, second derivative test, sign charts, those sorts of things, you always had equations with two variables in it. We have three variables, so similar to some of the related rates problems, you're going to have to use this other information to substitute for one of those variables. The most common related rates problems are when we use the cone problems. We had the volume of a cone, and you had volume equaled 1/3 pi r squared h, and you had to either get r or h in terms of each other. So that's similar here. We have to use this other information to solve for one of the variables. V x squared h. I have 108 my surface area equals x squared plus 4xh. Well, it's going to be way easier to solve for h here because there's only one h. Doesn't matter which one we solve for because we want to find the dimensions, so we're going to have to get both of them eventually. So you look at the equation, you say, okay, x is going to be pretty hard to solve for. We're going to have a radical in there. Let's do h. Subtract x squared from both sides, divide by 4x. The height of the box is 108 minus x squared over 4x. 108 over 4x is 27 over x. X squared over 4x is 1/4 x. The x cancels there. Break it down like this makes it a little easy to plug in the other equation. Using my secondary equation, using the given information, you were able to solve for one variable. Now take that and plug it into the other equation for that variable. So the volume is equal to x squared times the height, which is this expression. Distribute it through, clean it up a little bit. 27 over x times x squared. One of the x's will cancel, so you have 27x. 1/4 x times x squared is 1/4 x cubed. The minus sign stays. So your volume equals 27x minus 1/4 x cubed. Now you have an equation with two variables. Now it goes back to the exact same things you were doing. It goes back to the exact same things you were doing when you were finding max and min. You can forget about the word problem for now. Forget about all this. You want to find max. You want to find the maximum. So just pretend like this was the equation you were given. This is the equation you're given. Find the max point. So you're going to plug it, you're going to derive it. Find the critical numbers. And then see which ones give you a max. Copy the function over. First derivative, 27 minus 3/4 x squared. Want to find critical numbers. So you want to set the derivative equal to 0. If this was 0, I add this to the other side. So 27 equals 3/4 x squared. Divide by 3/4, you get 36 equal x squared. So x is plus or minus 6. Now we think about this problem. We're talking about a box. You're not going to have a box that's -6 inches long or wide or anything like that. So our only critical number is x equals 6. So that's where our max point occurs. If you test it with a sign chart, you would see that it will increase before, decrease after, so you would have a maximum at x equals 6. Now that we know where our maximum value is, x is 6, now you go back to the word problem. You want to find your dimensions, so you know your box is x by x on the bottom, but we got to find our height. Well, height equaled 108 minus x squared over 4x, so plug in 6 for x. Plug that in, you get 3. So your box was 6 by 6 by 3. So the idea is, read the word problem, determine what you're trying to maximize or minimize, determine what you're trying to optimize, use the information given to get you an equation in two variables for that value you're trying to optimize, then derive set equals 0, find your max point or find your min point. Once you get the equation, the problem's the same as what you've been doing. This was an example where we're trying to maximize something. I want to give you another example where we're trying to minimize a problem, or minimize a value. We want to minimize a distance here. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So we're going to find points on a graph that are closest to a point. Look at the picture here real quick. 4 minus x squared is an upside down parabola with a vertex at 0, 4. It wanted to know the value of the points closest to 0, 2. So I want to find the points on this curve that are closest to 0, 2. I want to know where they are. I've put a couple dots here. You can see that that they look like they're right in this area. With the symmetry of a parabola, you're going to have two. So you can see they're going to be somewhere in this area. You get a little far away up here, you get close, and you start getting farther away as you go down. So we're looking for those 2 points. We want the exact values. Obviously on a graph it's very difficult to tell those exact values, so we're going to use calculus to determine those. You want to find closest to the point. So you want the minimal distance. So you're going to use your distance formula. Distance equals square root x minus 0 squared plus y minus 2 squared. Distance between 0, 2 and some point x, y. When you have these questions asking about a graph, a lot of times your secondary equation is just going to be the equation of the function itself. So y equals 4 minus x squared. This is the function that I want to minimize. So I'm going to use this to get rid of y in this case. So I plug in 4 minus x squared in here. So you see that with 4 minus x squared plugged in. 4 minus 2. This becomes a 2 minus x squared. From here on out, it's just the calculus of simplifying this, then deriving it, and then finding the maximum. Once you get to here, once you combine those equations, you can forget about this until the end, until you get a value, then you got to think what that value means. Square this out first. So you get 4 minus 4x squared plus x to the fourth. When you square this out, so I have an x to the fourth. X squared minus 4x squared going to be negative 3x squared. That 4 stays as plus 4, and I wrote it to the 1/2, so it's a little easier to derive using the chain rule. Derive it. Half times this is a negative 1/2 times derivative of what's inside. Set it equal to 0. Where's the top equals 0? Where's the bottom equals 0 to find your undefined values for your derivative? In this case, the bottom never equals 0. There's no value if you use the quadratic. Well, you can't use the quadratic formula. If you graph this, you will see the function never goes through, never crosses the x-axis. So your only variables, your only values where the derivative is 0 come from the numerator. So you always want to factor out a 2x. So you're left with 2x times 2x cubed minus 3. X is 0. And if you solve this, add 3 divided by 2, square root both sides. X is square root plus or minus square root of 1.5 or 3/2. Now you go through and you try a sign chart at these 3 values. Down, increasing, decreasing, increasing. You're looking for your minimum, your closest value, so that happens at these 2 mins. So there are 2 points, which is what we expected when we looked at the graph because of the symmetry of a parabola. Negative square root of 1/2 or 3/2, positive square root of 3/2. In order to find a y value, you plug these back in the original equation to find y, and they give you the points closest to 0, 2. Five halves is 2.5, so at 2.5, at 2.5, right about where we said they would be. I went through this problem quick because the important part's not finding the derivative and finding the max and min. We've learned that all through Chapter 2 and Chapter 3. The important part is understanding how to relate this to these optimization problems. So here's a little bit of a set of guidelines for you. Identify what you're looking to find. What are you trying to maximize or minimize? What are you trying to optimize? Do you want to know the dimensions of a box? Do you want to know the radius of a sphere? Do you want to know the height of a cone? Do you want to know the distance between 2 points? All right? What are you trying to optimize? Know what you're looking for. And that would be your primary equation. Then read through the problem. They've got to give you some other information. If it was a graph like the last one, they're going to give you the equation of the curve. If they give you something about building something, usually they're going to give you some kind of measurement, where they have a certain amount of material to work with, whether it's a distance, or it's an area, or it's a volume. Whatever, and they will give you a specific value, a specific number, a specific amount. Whatever they give you the amount of, you're going to use that to develop as your secondary equation. You're going to combine them to get one equation by solving your secondary equation for one variable and then substituting it back into the original, the primary equation. Now you just go back to calculus. Take that new equation, find the maximum value. Just go through first derivative, set it equal to 0, find those values, and then answer the question. Right? Make sure you answer the question. Whatever they say. If they want to know the dimensions, well, when you found x, you also had to use that to find h. So you have to plug it back into a little more work to find the other values. Make sure you answer what they're asking for. Don't just get the max happens and x equals 2 and not realize, well, I have to do something with that 2 to actually answer the question. So be careful you answer the question at the end.